Okay, so today's class we are looking at topic 6, which is on generators and motors. But the first part of this topic we talk about electromagnetism. So we talked about batteries. That was our last topic. 1 second. And so what we talked about batteries was we were using them for portable power, like in watches, in flashlights, and so on. But their batteries, they don't have enough power. They can't supply the quantities of electricity that we need for like outdoor lighting equipment or heavy appliances and large industrial machinery. Most of our electricity that we receive, it comes from the conversion of mechanical energy. Mechanical energy, if you recall, it's associated with moving parts, right? Like a rotating windmill, the spinning turbines. Um, um, we saw previously the spinning turbines that we see in like thermoelectric power plants or nuclear or geothermal power plants. Even when we saw the hydroelectric power plants with the moving water of rivers or tides. So they're all associated with mechanical energy. An electric generator, this is a device that will convert the mechanical energy into electric energy. And this generator, its operation, it depends on the relationship between electricity and magnetism. So we start with a little bit of history. So the idea for the first electric generator, it dates back to a discovery by Hans Christian Ørsted and Andre Marie Ampere, and that was in 1820. So they started to notice this relationship between electricity and magnetism. So they would take a compass needle and a wire that was carrying electric current, and what they observed was the compass needle would move or it would turn when it was near a wire that was carrying electric current. The amount of deflection of that compass needle depended on how much electric current was flowing in the wire. And then if they reversed the direction of the current, the needle of the compass would move in the opposite direction. And if the current was interrupted, that magnetic effect would stop. So Hans Christian Ørsted, he was trying to show that there was no relationship between electricity and magnetism, but he observed the opposite when he was doing his observations with the compass needle and the wire carrying electric current. So that's electricity to magnetism. So here in this setup, so we have our battery and it's connected to a switch, and here we have the compass, and when there's electricity flowing through this wire, it's causing the compass needle to deflect or to turn or move. So that leads us to electromagnets. So when you take a soft iron core and you insert it into a coil of wire and a current is passed through the wire, you can get this strong temporary magnet, and it's called an electromagnet. And when electric current is flowing in the coil, one end becomes magnetic north pole, the other becomes the south pole. If you take more coils of wire and wrap it around the iron, the strength of the magnet increases even more. If you increase the current, it will also increase the strength of the magnet. If the direction of the current is reversed, the polarity of the magnet gets reversed. If you turn the current off altogether, the iron core, it loses its magnetic properties. So we've talked about the core being iron, the soft iron core, so that's really important as well. It depends on what material is used for core. Iron cores will be much more effective than using other metals or using other materials like wood or plastics at producing these strong electromagnets. So again, you can increase the coil of wire to increase the strength of the magnet. It depends on what you're using as the core. And it depends also on the strength of the electric current flowing through the coil. Okay, so here we're just looking at some simple electromagnets. So we have an electric power source. It's connected to a wire, and here inside here we have the soft iron core, and we can see like these paper clips are attached to it because it's magnetic. And here we can see similar setup, but we also see the north and south pole. So what are we seeing like when we're looking at particles or atoms? So individual atoms behave like tiny magnets. Each of them have a north and south pole. So even in iron, the atoms in materials like iron, cobalt, nickel, they group together into magnetic domains where all the north poles are facing the same way. Unmagnetized objects have domains that are randomly arranged, kind of like this. So this here is an unmagnetized material. This here is a magnetized material. All right, we can see the alignment, south and north, south and north, south and north for all of them, and so on. Therefore, that magnetic effect is strengthened. And if we look at iron, the magnetic domains in iron, they do line up very easily. So that's why iron is an effective core for these electromagnets. All right, so that was electricity to magnetism. Next, we're looking at magnetism to electricity. So we saw magnetic effects can be produced by electric currents, but the opposite process is also possible. Electric effects can be produced using a magnet. And this was discovered by Michael Faraday, an American scientist, as well as Joseph Henry, and in 1831. They were working independently, and they found that a voltage developed in wires that were moved at an angle to a nearby magnet. The same thing would happen when the magnet moved at an angle to a stationary wire. But if the motion stopped, or if the magnet and wire were moving parallel to each other, there was no voltage. So they extended their experiments by connecting the wire to a load. Now you would have an electric current flowing in a circuit. But as long as either the wire or the magnet were both moving, or as long as one of them is moving, they can have the production of electricity. As well, if you wrap the wire into coil around the magnet, it would increase the current. All right, so magnetism to electricity. So you either have to have the moving wire or you have to have a moving magnet, all right, to produce the electricity. So here the light bulb is on, light bulb is on. When there's no motion, the light bulb is off. All right, so when there is a relative motion between the wire and a magnet, there will be a current which will flow in a circuit connected to the wire. And it was this connection that was made between magnetism and electricity that was used to develop things like motors and generators and lots of other electrical technology. Even long before there was an understanding of what was happening. Okay, so I do have some videos here to show on electromagnetism, so I'm just going to pause here. Okay, so next we're talking about generators and motors. So here we're looking at a generator. So the AC generator is the most common form. There's a coil of wire that is rotating inside of a stationary field magnet. So here is the field magnet, and this is the coil of wire that will be rotating inside. It's rotated by an external force, usually supplied by steam or falling water or wind. And most larger generators, they're using electromagnets rather than permanent magnets. So this wire in the coil rotates and electrons will start to move along the wire in one direction. After 1/2 revolution of the wire loop, each side of the coil passes near the opposite pole of the magnet. Electrons in the coil will start moving in the other direction. The direction of the current from the generator changes twice with each revolution, and then this is why it's called an alternating current, because it changes direction, or it is alternating or alternates. Now keep in mind, in this type here, the wire is rotating inside a magnet, but we also know that current can also be produced when the magnet is rotated within the coil of wire. All right, and this is also using a hand crank model. This is a hand crank model. Why use AC or alternating current? It's relatively easy to increase or decrease the voltage of alternating current, and also in order to travel longer distances efficiently through transmission lines, the voltage is increased. So for consumer use, the voltage then has to be decreased. So that's why alternating current is used, and that's how it's supplied to our homes. This is a DC generator. I'm just going to pause it here. Okay, so next we're talking about this here, a DC generator. Generators can also produce direct current, which is current in only one direction. It's often called a dynamo when a generator produces direct current. There's an armature, so right here, this is the armature right inside of here. It's a rotating loop of wire. It's connected to the outside circuit by a split ring commutator, which is shown right here. We will be watching a video later which will show all of that in much more detail. All right, so here we have 4 positions here. Position 1, we have a brush that touches the metal split rings, so electrons are able to flow from and return to the armature. Then the armature and commutator rotate to position number 2. There's insulating gaps in the commutator which will momentarily stop the electric current. Then as the gaps move past the brushes, the current will resume. Then the direction of charge flow in the armature has reversed, but so has the connection through the commutator. So therefore the current continues through the load in a constant direction. Okay, and then same sequence of events repeats continuously as the armature keeps rotating past position 4. So electric motors can be constructed the same way as a generator. Instead of producing electricity, a motor uses electric energy, to make a coil of wire spin between the poles of a magnet, which is the field magnet. And that's occurring because the coil, which is the armature, is connected to a source of electric energy. Current that's flowing through the coil turns it into an electromagnet, which is then rotated by magnetic forces from the field magnet. And then the fundamental law of all magnets is that opposite poles attract, like poles repel, and that's the basis upon which electric motors will function. So DC motors in one common design, a rotating wire coil, which is the armature. It becomes an electromagnet as current flows into it through a split ring commutator. And again, the video will show this. The armature is attracted and repelled by stationary field magnets near it, so that's why it begins to rotate. The commutator kind of acts like a switch. It'll cut off and then reverse the direction of current flow, and that keeps the armature turning. So here's a DC motor. So here we have a DC motor, and it's rotated by magnetic forces between the field magnets and the armature. And the armature is acting as an electromagnet. So here is the armature. This is the field magnet. You can see the north and south poles. So electrons will start to flow to the right. So here we can see electrons flowing from the battery to the commutator. Here's the commutator, and then into the armature. There's the armature. So the north pole right here of the armature, it's repelled by the top of the field magnet, and it's attracted by the bottom, right? Because that's the south. And so therefore the armature will begin to rotate clockwise. Okay, if you follow this yellow dot, it shows you the rotation. Then the commutator will cut off the current so that the armature does not stall as it passes close by the field magnets. The momentum of the spinning armature, it keeps it moving clockwise. All right, so there's the yellow dot. Then the commutator, it reverses the direction of the current through the armature. The ends of the armature, they'll reverse their magnetic polarity. The top of the armature is now getting repelled by the top of the field magnet, but it's attracted by the bottom of the field magnet. And so that is the reason why it'll continue to rotate it clockwise. AC motors are electric motors. They are found in larger appliances like dishwashers, washing machines, garage door openers, furnaces, and they operate it on alternating current. So they have a rotating core. It's called a rotor, and it's made up of a ring of non-magnetic conducting wires connected at the ends right here and held usually in a laminated steel cylinder. So this here is the rotor. And then surrounding the rotor is a stationary component called the stator or the stator right here. Okay, so rotor is rotating, the stator is stationary. So simplest form, the stator, it's a two-pole electromagnet, so north and south. There's more complex stators that resemble a ring of many electromagnets, but each will still have a north and south magnetic pole. So when an AC motor is turned on, the attraction and repulsion between those magnetic poles of the stator and the rotor will cause that rotor to spin. All right, so again, these are used in larger appliances. Okay, so I do have a video here, so I'm going to pause here on how does electric motor work.